Pan American World Airways once stood like a lighthouse on the edge of a new age, its beacons showing the world how to cross oceans not by ship, but by air. For a long stretch of the 20th century, people simply called it the airline that taught the world to fly. Its beginnings reached back to the late 1920s, when a daring partnership formed between Juan Trippe, a young strategist with a global imagination, and Charles Lindbergh, the pilot whose solo leap across the Atlantic had made the impossible feel ordinary. Together they turned a private vision into a public pathway, a network designed to spread commercial air travel across borders and into the daily lives of Americans. Through the decades that followed, Pan Am's blue globe became a symbol, and until the early 1970s, the airline sat at the peak of the commercial transport industry, setting standards others tried to match. But tides change, even for giants. In 1973, the price of oil climbed in a sudden, punishing surge. By the following year, the largest airline in the United States found itself pressed to the cliff's edge of bankruptcy. L.H. Allen, Pan Am's vice president and chief engineer, said the quiet part aloud. When the fuel bill reached 40 cents a gallon, efficiency became not just a good idea, but the single most important factor in the way an aircraft should be designed, flown, and maintained. If the airline was to survive, it would have to squeeze more miles from each drop. That is why Allen and his team reached out to the NASA Center in Cleveland, then called the Lewis Research Center, and to a national effort known as the Aircraft Energy Efficiency Program. Together, they went searching for practical ways to make engines sip rather than gulp. At Lewis, engineers ran their own family of fuel efficiency projects under that larger umbrella. The first, called Engine Component Improvement, took a clear-eyed look at the turbofan engines already flying. Instead of dreaming up entirely new machines, the team focused on the parts most likely to wear down and drag performance with them. Change the blade here, redesign a seal there, reduce the kind of erosion that eats away at efficiency, and the numbers across the fleet could improve. It was an attempt to cure sick engines rather than build new bodies. Pan Am invested in every incremental gain that could keep aircraft economically airborne, served as a chief independent evaluator and one of the program's strongest supporters. The aim was modest on paper, a 5% improvement in fuel efficiency over the life of the engines. But in the world of airline finance, 5% could mean the difference between thin profit and deep loss. Alongside that, a second project called the Energy Efficient Engine, shortened to E3, imagined a clean slate. Start from scratch, rethink every pressure ratio and airflow, and aim for 10 to 15% better efficiency. If the component program was a patch for today, E3 was a blueprint for tomorrow. Together they formed the core of the Lewis propulsion work within the energy efficiency push. A third effort, the advanced turboprop, would later spark debates and disagreements, but that part of the story belongs further on. Pan Am's collaboration with NASA's engineers produced methods and data that did what they could. The airline's fortunes, however, had been linked to the price of fuel in a way that no innovation could quickly untangle. In January 1991, after years of trying to find altitude in turbulent air, Pan Am declared bankruptcy. Historians would later point to the world oil crisis as the blow from which the company never truly recovered. The airplane that had taught others to fly, it turned out, was also a student of the same harsh lesson. Energy drives flight, and energy's price can ground dreams. To understand how NASA's Cleveland laboratory stepped into that story, it helps to let the clock run backward. The Lewis Research Center had been founded in the heat of World War II as a laboratory devoted to aircraft engines. It was the third field laboratory under the National Advisory Committee for Aeronautics, following Langley in Virginia and Ames in California. At Lewis, the mission was clear and patriotic: push engine technology forward in the national interest. That work did not always sit comfortably with private engine builders, who sometimes saw government researchers as intruding on a marketplace that, they believed, should be left alone to find its own equilibrium. Yet the lab's contributions mattered, especially as the early Cold War years pressed US companies to master the turbojet. Lewis researchers tested, measured, and shared, nudging designs toward reliability and power. Then, in 1957, the beeping radio call of Sputnik cut through the air. The nation turned its attention outward, above the atmosphere. Lewis pivoted with it. For nearly a decade, the laboratory left behind air-breathing engines to concentrate on rocket propulsion, combustion for the vacuum of space. When the era of giant space programs began to taper, staff cuts came like a cold front. By 1972, nearly 800 people had left. The centre sought a new identity that could secure its budgets and steady its purpose. In 1973, the federal budget for NASA fell further. In the same season, the oil embargo announced that fuel would be expensive, uncertain, and politically freighted. Bruce Lundin, the centre's director, looked at his facility, not just the buildings and rigs, but the minds and methods inside, and asked how that propulsion expertise could be turned toward a national emergency that was now on the ground as well as above it. Engineers had already begun to look earthward. Within the laboratory, a volunteer group formed to reduce energy waste and raise conservation awareness. Louis Rosenblum and J. Stuart Fordyce led these efforts, motivated in part by the shame and symbolism of a river in Cleveland catching fire, a headline that had made a city the butt of jokes and a country face a truth about pollution. Robert Hibbard, another engineer, started a graduate seminar that brought in students from nearby universities to ask and answer practical questions. How do you make engines cleaner? How do you deal with real environmental complications rather than theoretical ones? In 1971, the centre opened an environmental research office. Monitoring stations popped up around the city to collect data. The engineering culture that had always measured heat and pressure and efficiency began to measure particulates and water quality. The centre worked with the nascent Environmental Protection Agency to study Lake Erie, and at Plumbrook Station, the centre's outpost, a nuclear test reactor irradiated samples for EPA studies by the thousand each year. Seeds were being planted. When you follow the lines, you can see a propulsion lab learning to speak the language of energy and environment. From that soil, new projects grew. In 1974, the centre secured funding for wind energy research from the National Science Foundation and the Energy Research and Development Administration. That money didn't go into wish lists, it went into metal and bolts and blades. At Plumbrook, engineers constructed experimental windmills not as icons but as instruments. The first stood 125 feet tall, with 2 propeller blades, each 62 feet long. It could generate 100 kilowatts, a notable output for a machine built to learn. At the time, only one windmill anywhere in the United States was larger. People working on those blades believed they were looking at the country's future and said so. They imagined hills and plains dotted with turning rotors, hundreds of thousands of them feeding power into the grid. Years later, in 1988, a Lewis-managed team would help build what was then the world's largest commercial wind turbine in Hawaii. The idea made concrete in steel and fiberglass. Almost as soon as the wind project caught air, a solar program followed. The centre advanced solar cell technology, built expertise, and became known enough that when the federal government considered sites for a large solar research institute, Lewis was in the discussion. It did not win the institute, but the work continued, and in 1978 the centre's engineers were called on to help create the first solar power system designed to serve an entire community. The place was a small Papago village in the desert of Arizona, roughly 100 miles northwest of Tucson. Rosenblum designed the array and helped install it. There the sun replaced kerosene, raising lights in 16 homes, a church, and the tribe's feast house. The change was practical, not symbolic. Cleaner, steadier, safer light. One more demonstration that energy work could alter daily life. Electric vehicles also passed across the drafting boards. The hybrid vehicle project aimed to study concepts that would leave a smaller exhaust trail and travel more miles on fewer fossil fuels. These were primarily electric vehicles charged from external sources, the kind of everyday car that might be practical if batteries and systems could be made trustworthy and affordable. In 1975, when the centre completed its initial plan and began talking with ERDA about the research, a Washington Post article summed up the hope plainly. This work could make electric vehicles practical and reduce the nation's dependence on foreign oil. Possibilities started to feel like a plan. The very fact that a NASA center was working so broadly in energy stoked rumors. Would the laboratory leave its home agency and become part of ERDA? Some reports even asked whether it should continue its aeronautics propulsion work at all. The engineers answered with action. In December 1974, they organized and formed the Engineers and Scientists Association, joining a professional federation that gave them a voice as they navigated their future. Equally important, they turned back toward what they knew best, engines, and looked for a mandate that could keep them both useful and firmly within NASA's orbit. They found it in a national requirement that was as concrete as a runway. Build aircraft engines that use less fuel. Energy-efficient flight would be the way to keep the laboratory's heritage alive while serving a problem that every airline accountant could understand. It would also give aeronautics a fresh moment in the spotlight at an agency whose headlines mostly celebrated space. From 1973 to 1976, the pace was relentless. Donald Norrid, who led the Lewis portion of the aircraft energy program, remembered it as a time of quick studies, hard choices, and a supportive climate driven by obvious national need. The center explored concepts on paper and in test cells, chasing techniques that might save fuel without sacrificing safety or performance. Because the people involved talked to one another constantly, engineers in Cleveland, planners at NASA headquarters, designers at engine companies, the lineages of individual ideas are sometimes tangled. What matters is that during those years, the outlines of 3 major projects came into focus. Develop advanced turboprops, design a new energy-efficient core engine, and study why engines lose performance over time so that the losses can be slowed or reversed. Even before those projects had names, NASA had launched a study called Energy Trends and Alternative Fuels in April 1973. Headquarters managed it, with Lewis and Ames contributing, and Abe Silverstein, who had once directed the Lewis Center, chaired a committee on aircraft fuels. The goal was practical: measure likely future fuel needs and explore alternatives. By the end of the year, the discussions had pivoted from exploration to recommendation. It was time to propose specific programs, not just to consider whether aircraft could burn different fuels, but how to conserve fuel with the technologies already available or within reach. In January 1974, a steering committee met to turn those broad goals into a plan. They looked at designs, listed the technologies that could save fuel, and ran trade studies to show what the gains might cost in dollars and schedule. After just a month, they produced a map for a 9-year research effort they named the Energy Conservative Aircraft Propulsion Technology Program. $136 million would be needed, they calculated. A major pillar of that plan would be a new kind of efficient engine. Some estimates suggested 30% better than existing power plants, possibly ready for service by the middle of the 1980s if industry embraced the advances. That notion became the Energy Efficient Engine Program. The advanced turboprop line of work, meanwhile, traced its inspiration to a workshop held by the American Institute of Aeronautics and Astronautics in March 1974. Engineers and researchers there concluded that modern propeller systems, redesigned with new aerodynamics and materials, could save around 15% more fuel compared with the jet engines that were then standard on many routes. Another line, engine component improvement, began to coalesce in the summer of 1974 when Lewis paid American Airlines to open its records. The goal was simple and powerful. Study how engines such as the JT9D and JT9D actually degraded in service. How fast did their performance decline, and why? With those records in hand, and a related contract with Pratt & Whitney to study deterioration on its current engines, the program obtained the early evidence it needed. By January 1975, Pratt & Whitney brought forward its findings, and a coordinating group known informally as the Kramer Committee stepped in to keep all the threads aligned, across NASA headquarters, the budget offices in Washington, and advisory boards in industry. The committee's careful shepherding helped the broader energy efficiency program avoid bureaucratic stalls and move into the work of building, testing, and proving. Engine component improvement, ECI for short, sat squarely on the desk of Raymond Colliday when it came time to turn proposals into contracts and experiments into deliverables. Colliday had joined Lewis in 1969, then later moved to NASA headquarters and would eventually lead the Defense Advanced Research Projects Agency. In those early ACE days, he remembered, Congress was receptive. In a time of energy worries, lawmakers favored research that promised practical savings. The more complicated conversations happened with the Office of Management and Budget. The philosophical question there was where the government should draw its line, supporting long-term research, yes, but not stepping across into developing specific products for private industry. Most of the ACE portfolio eased past that concern. ECI, however, touched existing commercial engines. It sharpened the edge of the argument. If NASA helped improve parts inside current engines, was that crossing into company territory? Those debates shaped how the program was structured, but did not stop the work. From the beginning, ECI was designed to deliver results on a short runway. Other projects assumed a decade or more between research and airline service. ECI aimed at 5 years. No one promised dramatic revolutionary changes. The plan was to identify the components most likely to undercut efficiency as an engine aged, then fix them so that airplanes would hold their performance longer between overhauls. The companies that made most of the commercial engines in US service in the 1970s, Pratt & Whitney and General Electric, worked with NASA closely, their teams mixing in test cells, data rooms, and conference tables. A formal statement of work in late 1976 put the goals succinctly: develop ideas to improve and retain performance so that new production engines in the 1980-1982 period would save about 5% fuel over their service life and generate additional technology to minimize how much performance fades in both current and future engines. To appreciate the scale, consider what flew then. In 1976, 4 families of jet engines carried nearly all commercial passengers and cargo in the United States. Together, they burned around 10 billion gallons of fuel each year. ECI focused on 3 of those families: Pratt & Whitney's JT9D and JT9D, and General Electric's CF6. The 4th, the JT9D, had been widespread but was on the way out of production, so it was left out of the improvement package. The JT9D had arrived in 1964 and became a staple of the jet age, powering fleets of narrow-body airplanes as a reliable workhorse engine. It earned the label of a phenomenal success, installed across thousands of aircraft in multiple types and variants. 2 years later, Pratt & Whitney brought out the JT9D. It opened a new era in commercial flight by giving wide-body aircraft a high-bypass turbofan with the thrust and efficiency required to carry hundreds of passengers across continents and oceans. The Boeing 747 became the public face of that era, and in April 1966, Pan American placed the first order for the new giant, its future tied to the promise that the JT9D embodied. General Electric's CF6, which debuted in 1971, powered the DC-10 and matured into the anchor of GE's wide-body engine business, staying relevant for more than 30 years as new airframes and upgrades came along. The circle of names around the Engine Component Improvement Program looked in 1977 like a directory of American aviation. NASA's contracts, signed that February, went straight to the two giants of the day, General Electric and Pratt & Whitney. Those awards came with a string attached, not hidden but deliberate. Because both manufacturers would likely profit from any improvement flowing out of NASA's research, the agreements included a payback clause. Each time a fuel-saving component born from the program entered service, 10% of the sales value was to be returned to the US Treasury. It was a practical concession to policy skeptics in Washington. The Office of Management and Budget could approve an effort that touched commercial products if the public, which had funded the work, was guaranteed a measure of return. The accounting would be messy enough that one of NASA's program leaders would later shrug and call the clause more trouble than it was worth. The money, when it did arrive, did not go back to NASA but disappeared into the Treasury's general flow. Still, the clause had done its job at the time. It opened the gate. From those primary contracts, tributaries spread. GE and Pratt & Whitney reached into the airline world and the factories where airframes took shape. Subcontracts went to American Airlines, Trans World Airlines, United Airlines, Douglas Aircraft, and Boeing. The NASA Center in Cleveland, still widely known as Lewis, also engaged Pan American and Eastern. Those two carriers, one with its eyes on global routes and the other focused on domestic patterns, would serve as independent reviewers. Outside voices asked to evaluate the work over 2.5 years and keep the program grounded in operational reality. All the agreements were framed around 3 recurring tasks that would echo throughout the life of the project. First, study the feasibility of ideas. Second, build and test parts in controlled facilities. Third, put changes on actual airplanes for in-service and flight tests. The broad participation was not a bureaucratic accident. The program leaders wanted every major player in the US industry to feel invested and to be ready, when results appeared promising, to adopt the improvements quickly. Of course, when competitors sit at the same table, the air can get tight. Pratt & Whitney and General Electric were not simply brands. They were rivals with long memories. For years after the war, Pratt & Whitney had been the default name in commercial engines, while GE's strength lay more with military work. Those borders had shifted with technology and markets. By the late 1970s, GE was gaining ground in the airline arena. The stage was set for what, in the early 1980s, observers would call a great engine war. Sales campaigns pitched city by city, airline by airline, each company arguing that its thrust and efficiency and maintenance economics were better. Against that backdrop, collaboration could feel unnatural. From the NASA side, managers noticed more friction with one company than the other. Pratt & Whitney, facing pressure from GE in a segment it had once dominated, bristled at the openness that government research can require. Freedom of information laws and NASA's culture of publishing test results meant, in practice, that data did not stay locked in a single corporate vault. NASA officials heard that Pratt & Whitney wanted to draw proprietary curtains around almost everything. The company also pushed at times for public support that would bolster the near-term sales of its engines. None of that was unexpected. It was the posture of a firm in a hard fight. Yet the NASA team reminded all participants that the program, by design, involved sharing methods and measurements. GE did not object on principle to that transparency. The message to Pratt & Whitney was simple, if not comfortable. To gain the benefits of this government industry effort, everyone would have to accept a looser grip on information than private habit might prefer. Underneath the politics, the work moved with a steady rhythm. ECI broke naturally into two lines: performance improvement and engine diagnostics. The first line was a kind of triage on paper and then in metal. Engineers began with a feasibility sweep through a wide field of concepts, from small seal changes to aerodynamic revisions deep in the core. The first pass asked two big questions over and over. Will it work, and will it pay? Those questions branched into detailed criteria. On the technical side, the group scored ideas for raw performance impact, added weight, maintenance implications, potential savings in fuel, compatibility with materials already in use, time required to develop and certify, and the inherent risk in trying to turn a drawing into a reliable part. On the economic side, they created and adjusted models. What would fuel cost? What would a modified engine cost to build? How many would be produced? How would airline operating costs move in response? When would the investment be returned? And how long would the part live in service? The carriers involved were not there only for show. They rated the practicality and desirability of changes because they were the ones who would live with them on the line. The funnel was narrow. For Pratt & Whitney's engines, 95 ideas went into the evaluation mill. For GE's CF6, 58. The initial screen cut those down quickly to clusters that seemed likely. 18 on one side, 29 on the other. NASA and airline reviewers then pored over the survivors. From that second pass, they selected 16 candidates that looked promising enough to justify prototyping, test cell time, and ultimately installation on a flying aircraft. What those 16 efforts targeted can be grouped in a few plain categories. The first, deceptively simple to say and maddening to perfect, was sealing leaks. A turbojet or turbofan is, at heart, a pressure machine. If air leaks internally, if hot gases slip past where they are meant to do work, efficiency drains away like water from a cracked bucket. Better seals, tighter clearances, smarter ways to manage the gaps between parts that grow and shrink with temperature and rotational speed. These could all guard the pressure that the compressor had worked to build. The second category was pure aerodynamics, sculpting blades and vanes so that they did their work with less drag and loss, both in compressors that raise pressure and turbines that extract work from the hot gas stream. A third concerned heat and the materials that face it. Ceramic coatings could protect metal from the furnace of the turbine and, crucially, might allow engineers to close some of the cooling holes that bled precious air away from the main flow. With a good thermal barrier on the surface, you could reduce the amount of cool air that must be siphoned through internal passages. The less parasitic cooling you need, the more of the compressor's output is available to make thrust. In practice, the list was specific. On the Pratt & Whitney JT9D, engineers pursued an improved high-pressure turbine air seal, a redesigned high-pressure turbine blade, and a high-pressure compressor with trench tips to control leakage. On the JT9D, They pushed several changes around the high-pressure turbine, an outer seal backed by ceramic material, a thermal barrier coat on hot parts, and an active clearance control system to keep gaps tight as temperatures shifted. They also worked on a new fan design. For GE's CF6, the set included a new fan of its own, a revised front mount for the engine, a short-core exhaust nozzle to clean up the flow, aerodynamic refinements in the high-pressure turbine, a system to better maintain circularity, roundness, in the turbine structure, and another application of active clearance control in the turbine. 2 aircraft-level changes rounded out the package, a nacelle drag reduction for the DC-9 and a reduction of compressor bleed air on the DC-10. What united all of these was the aim to save fuel without rewriting the fundamental architecture of the engines or the airframes. Results came quickly enough to be noticed. Within only a few years, improved pieces were flying. Industry writers at the time remarked that by 1982, many of these components were already at work, trimming fuel consumption and giving their makers a strategic edge as foreign competitors pressed into markets that American companies had long considered home. It was not just the parts themselves, but the pace of proving and certification that mattered. Speed favored those who had a credible story to tell an airline trying to make its next billion-dollar fleet choice. The second half of ECI, engine diagnostics, took a different posture. Think of it as medicine for machines. Pan Am's engineers, participating closely, believed this line was the most significant of all. Its emblem, drawn for internal briefings, showed a weary engine as a cartoon patient, tongue out, belly clutched, while a country doctor peered at an X-ray. Silly as that sketch was, it pointed to the real question: why do engines fade as they age? And what can you do about it? The sickness was not a single failure, but a long list of small degradations. Combustors creep and warp after countless heat cycles, forever expanding and contracting. Compressor blade tips wear, opening up tiny paths where air can leak. Seals that once hugged tightly begin to pass hot gas. Turbine blades erode under heat and stress. Then there were the insults from outside. Pebbles or sand sucked from a runway, ice or grit tapped into the leading edges, small dents that slightly change the shape of a blade, and, with it, the way air moves over it. None of this meant danger. Modern engines are built with vast safety margins, but over, say, 10,000 hours before a major shop visit, these small changes can add up to a steady drift downward in efficiency. And when the engine comes apart for its big overhaul, the rebuild does not always return it, in fuel burn terms, to the state it had on day one. Before the diagnostics push, much of what operators and manufacturers said about deterioration drew on experience and educated guesswork. The program's goal was to replace folklore with measurement. NASA's team and their counterparts at GE and Pratt & Whitney gathered data in bulk. In-flight recordings captured how the engines behaved in service. Ground tests provided controlled baselines, and maintenance records revealed which parts failed or were replaced and how often. For the JT9D and CF6 in particular, the program supplemented the existing files with special monitoring instrumentation, and, in some cases, full teardowns followed by meticulous inspection and measurement. Ground tests were devised to simulate particular operating conditions, short-term and long-term, that might accelerate certain modes of wear. Piece by piece, a picture formed. The teams could point to components with failure rates or loss patterns that made them prime candidates for redesign. That map, in turn, fed back into the performance improvement side. Fix what hurts most. As the diagnostics findings accumulated, a fresh kind of tension surfaced. Pratt & Whitney worried that the deterioration story of its engines, told in data and graphs rather than corporate slogans, was being weaponized by competitors. The company's public promise had long been dependable engines, and the thought of seeing detailed curves about performance fade in flight hours made their marketing staff uneasy. There were reports, too, that a British rival, Rolls-Royce, had used published ECI data on the JT9D and CF6 to make a case for the relative virtues of its own models. In 1979, Pratt & Whitney's lawyers wrote to NASA about the risk that open dissemination of the program's reports might undercut the company's position. They asked that circulation policies be reconsidered to protect their marketing. NASA's response was steady rather than defensive. The agency acknowledged the side effects of transparency, but reminded the company that participation had been voluntary from the start and supported by its management. The understanding at kickoff was clear. The program would compare engines and publish results. Both GE and Pratt & Whitney had accepted those terms. The logic behind that openness remained intact. If the goal was to lift the fuel economy of the whole US fleet, the right path was to let engineers and operators across the industry see and use what the measurements revealed. The independent reviews by Pan American and Eastern became a vital mirror. Pan Am's reports drew on 10 meetings across the life of the project. At each session, teams from NASA, GE and Pratt & Whitney summarized their progress for an airline committee that was charged with asking practical, sometimes pointed questions. The first meeting, held at John F. Kennedy Airport in March 1977, set the tone. Introductions made. Scope agreed. Objectives sketched. By the 6th, in September 1978, Pan Am's tone had sharpened. The airline described the program to that point as disappointing and urged the engineers to push beyond what felt like a cautious, incremental path. They preferred a bolder, even aggressive stance that promised larger payoffs. They also warned that some participants appeared to be drifting away from the program's basic objective of saving fuel in service. Those criticisms stung. They also had effect. As the work advanced and test results accumulated, Pan Am's later reviews gave credit where it felt due. By the end, they praised the program for adding significant knowledge that could be put to use and judged it, on balance, as success. If you enjoy drifting off to calm, true stories about technology and the people who shape it, consider subscribing to and liking Space Historian. It helps these gentle deep dives find you again the next night. What made ECI stand out among the broader energy efficiency efforts was not only what it discovered, but how quickly the discoveries were adopted. While other projects chased larger percentage gains that would take a decade or more to mature, ECI's modifications slipped into production and fleets with unusual speed. In January 1980, roughly 3 years after the program began, its performance improvement lead stood before an audience at the Aerospace Sciences meeting with results in hand. The message was encouraging. The work had already created a meaningful potential for lowering the commercial fleet's fuel consumption, and there remained room for additional savings as studies continued. By the spring of that year, the paper trail was thick. Dozens of technical papers, contractor reports, memorandums, conference contributions, and journal articles laid out the methods and the math so that others could follow. Endorsements arrived not just from journals, but from executives whose factories built engines used every day. A senior leader at GE wrote to the director of the Lewis Center to emphasize the program's value. He called the knowledge generated a wealth, and he stressed that the ultimate beneficiaries were the airlines that would burn less fuel per hour. He even put a number to it. On the CF6, he estimated, the changes translated to a reduction of about 10 gallons for each hour flown. In a business where every hour is replicated across thousands of engines and millions of flights, those gallons add up. There was also a competitive dimension that mattered beyond individual companies. Boeing, looking outward to international sales campaigns, approached NASA in early 1980 with a straightforward request. Could the manufacturer share ECI results with foreign airlines to demonstrate that American industry held a more precise understanding of how engines degrade and how to slow that slide? NASA agreed. The reasoning was strategic and national. To meet foreign competition, US airframers needed to show that their products incorporated the most current proven technology. By letting the research flow into the sales conversation, the agency supported the broader aim of keeping the domestic industry strong. Observers of the field saw the downstream effects. New airliners of the early 1980s, including Boeing's 767 and McDonnell Douglas's MD-80 series, flew with engines that had taken in many of ECI's advances. None of this was surprising to those inside the program. ECI had never promised the dramatic gains sought by the energy-efficient engine initiative or by later radical designs. Its pledge was modest and precise, roughly a 5% reduction in fuel use across the life of the engines it touched. And on that measured goal, the engineers finished where they had begun, by delivering exactly what they had projected at the onset of the program. By the early 1980s, the business of flying had grown complicated and brittle. Airlines that once seemed unshakable were caught in crosswinds they hadn't faced before. Profits thinned. Fuel prices rose and fell like restless tides. Wages climbed with the cost of living. And deregulation rewired the market so that routes and fares became a ceaseless chess match. Across the Atlantic and Pacific, competition pressed in as well. The names that had defined American engine making, Pratt & Whitney and General Electric, were not just selling hardware, they were locked in campaigns where every decimal of efficiency and every dollar of price might tip an order. Meanwhile, the British firm Rolls-Royce, buoyed by its government, pushed hard into the global arena. In that atmosphere, even giants found themselves fighting to breathe, and Pan Am, the airline that had once knit continents together with its roots, was among those struggling to keep altitude. Yet inside that turbulence, a quiet strand of optimism emerged. A 1983 report noted that the future of the industry, while far from easy, might look a shade brighter. The reason given was not a single dramatic airplane or a flashy new route, but a patient, less noticed effort aimed at the heart of the machine, the engine itself. At NASA's Lewis Research Center in Cleveland, the same group that had worked with airlines on the Engine Component Improvement Project was guiding a parallel endeavor that asked a bolder question. What if, instead of patching wear and tear, you could redraw a modern turbofan from a clean sheet so that it used meaningfully less fuel, ran quieter, and met tough emissions with room to spare? The effort carried a compact name, E3 for Energy Efficient Engine, but its ambitions were expansive. Forbes would later call it a NASA success story that simply didn't shout as loudly as the space program. The pairing at the center of E3 felt improbable precisely because it was so necessary. Pratt & Whitney and General Electric were fierce rivals, and yet, like climbers roped together on a difficult face, they were asked to explore different routes toward the same summit. Each company had sketches and theories for getting more miles from a kilogram of fuel. Neither could easily justify, on its own, the cost and risk of developing those theories into hardware. NASA stepped in as a steadying hand. The agency put up $90 million for each company to pursue its approach, and asked that each firm bring $10 million of its own money to the table. It also framed clear goals: reduce fuel consumption by around 12%, trim operating costs by 5%, satisfy the Federal Aviation Administration's noise limits, and meet the environmental standards proposed by the Environmental Protection Agency. The engine would need to be rugged, safe, and lighter by about 10%. minimum takeoff thrust targets would keep the designs honest about real-world performance. For comparison, the familiar workhorses, Pratt & Whitney's JT9D and GE's CF6, served as the benchmarks. As before, NASA didn't work in isolation. Airframe builders, Boeing, McDonnell Douglas, and Lockheed joined as partners to ensure engines and airplanes would talk to each other cleanly. Eastern Airlines and Pan Am stayed close as advisors, bringing the voice of day-to-day operations into the room. Inside NASA, the program was managed by Carl Chipluck at Lewis, with Raymond Colliday helping to steer at key moments. On the company side, Ray Busey led the effort at GE, while W.B. Gardner did the same at Pratt & Whitney. Busey spoke of the program in simple, eager terms. This work was guiding the future of aircraft engines. Fuel-efficient flight required complex, expensive research, he said, but the reward could be counted out plainly, on the order of 1 million gallons of fuel saved per aircraft per year. Gardner, for his part, believed the results could run ahead of the stated targets. If you like drifting off to a calm, true story like this, where technology meets patience and people turn hard problems into small, steady gains, tap subscribe and like on Space Historian. It helps this kind of peaceful exploration find you again the next night. At the center of the E3 idea sat a machine whose basic form is easy to picture. A turbojet makes thrust by burning fuel and throwing mass backward. A turbofan is a turbojet with a wide, multi-bladed fan at its nose. Some of the air the fan moves continues through the hot, high-pressure core. The rest bypasses that core and flows around it in a cooler stream. The ratio of bypass air to core air, 4:1, 5:1, or higher in later engines, defines what we call a high bypass engine. Those engines, which came of age in the 1960s and 1970s, changed commercial flight by marrying thrust with efficiency. They promised more miles from the same fuel and a smoother ride for people and freight. But they also came with challenges. Big fans made big noise unless designed very carefully, and pushing temperatures and pressures high enough for true efficiency demanded close attention to emissions. E3's purpose was to meet those challenges head-on and harness the full potential of the high-bypass turbofan. The seeds had been planted earlier. In 1974, 2 substantial studies laid out the terrain. One, led by GE, examined turbofans designed expressly for low energy consumption. Another, led by Pratt & Whitney, explored unconventional engine ideas that might underpin the next leap in efficiency. Both pointed the same way. There was real promise here. But each study also told an inconvenient truth. Bringing such designs to life would cost a great deal of money and, even if things went smoothly, take a decade or more. Private companies could not share the results broadly if they paid for all of the risk themselves. The normal logic of competition would keep much of the learning behind walls. NASA's involvement changed that equation. With public funding and coordination, the results could be published, shared, and used across the industry. As Colliday and Neil Saunders later wrote, the promise shown in those studies justified initiating the energy-efficient engine project. To keep expectations realistic, NASA defined the E3 engines not as final products, but as experimental platforms. They were to be places where ideas could be proven and measured, not production line models ready for airlines. The components on the table ranged across the full flow path and structure: fans, compressors, turbines, flow mixers, the shapes and coatings that would line the gas path, lighter frames and casings, improved blade designs, and the clever management of clearances, the tiny gaps that decide whether air does its work or leaks away. Both companies had the same destination. The routes they chose reflected their different instincts. Pratt & Whitney leaned toward a component-first strategy, attacking the high-pressure turbine so that it could do its job efficiently at lower hot gas temperatures. Lower temperature, if achieved without losses elsewhere, meant less need for cooling air and a gentler life for materials. GE chose a more integrated approach, examining the way a new fan, a high-pressure compressor, and a low-pressure turbine could be tuned as a system. The gift of a clean sheet, as writer Jeffrey Ethel observed, let both firms step outside the slow pace of incremental change and venture into riskier, more ambitious territory. Around these engines in progress, the circle of partners widened. Boeing, Douglas, and Lockheed provided mission definitions and the pragmatic details of installation and integration, how a nacelle wraps around an engine, how flows mix at the tail, how the engine's weight and vibration interact with an airframe. Eastern and Pan Am stayed in the loop, looking at each proposed gain with the sharp eye of people responsible for schedules, maintenance, and costs. NASA kept its own labs busy too, feeding in-house research and specialized contractors into particular needs as they arose. The agency never intended to deliver a new engine to market. That was the manufacturer's job, but the lessons learned in ECI, better fans, better seals, smarter mixers, and the measurements from the engine diagnostics effort, how and why engines fade in service, flowed into E3's designs, shortening the path from idea to hardware. Because the list of ambitions was long, NASA asked for a clear-eyed look at risk before work accelerated. In April 1976, James Kramer, who directed the overall Energy Efficiency Office, wrote to Donald Norrid at Lewis and requested a risk assessment for the whole E3 plan. When Norrid answered 2 months later, he did not sugarcoat the view. Programs on the frontiers of technology are, by their nature, high risk. There is no way to turn them into safe bets. The best approach to reduce that risk, he wrote, was to fund multiple contractors so that different ideas could run in parallel. Each company would carry its own set of challenges. With both shouldering the work, the program stood a very good chance of delivering at least half, and perhaps more, of its stated performance goals. One of the enabling advances that arrived early was digital control. Engines had long used hydromechanical systems to meter fuel and coordinate vanes and valves. E3 absorbed a newer brain, full authority digital electronic control, FADEC, capable of watching over 10 engine parameters at once and communicating with the cockpit. Sensors, notoriously one of the most fragile parts on an engine, could fail. FADEC used a mathematical model to predict what the engine should be doing under any given condition. If a sensor dropped out, the controller could infer the missing value from the model and keep the machine running properly. It was a quiet revolution in the black boxes mounted on the side of the nacelle, one that rippled through reliability and ease of operation. Then, in 1982, budgets tightened. The program was redirected to fit a slimmer outline. Cecil C. Rosen, managing the propulsion office at Lewis, explained what that meant. GE would proceed with testing of its core engine, the heart of the machine where pressures and temperatures were highest, but pause work on detailed emissions trials and on a fully updated flight propulsion system. Pratt & Whitney, conversely, would continue concentrating on component technologies rather than a whole engine evaluation. The reshaping of effort carried an uncomfortable side effect. Because Pratt & Whitney had more component work left to do under this plan, more funding would, for a time, tilt its way. That unevenness was not what the program had intended at the start, but Rosen hoped it would be accepted as a practical compromise. GE's path through the redirected program produced a strong finish. By 1983, observers were calling its E3 turbofan the world's most fuel-efficient, best-performing engine of its class. Boosie, the GE program manager, said it was one of the most successful efforts on an all-new engine in years. The aerodynamic design of the low-pressure turbine, the set of stages that harvests work from cooler, slower gas after the core has done its job, had been a hard problem. The team solved it to NASA's demanding targets. Measured against the CF6 style baseline, GE's E3 delivered about a 13% improvement in fuel efficiency, beating the 12% requirement by a point. That margin matters in engineering as much as in sports. It meant breathing room for real-world variation. GE didn't leave the results in a report. The company moved the tested ideas into engines that would fly for decades. The CF680E, which would power the Airbus A330, and the JT9D, designed for Boeing's 777. When the JT9D first caught headlines in 1991, the interest was not just in its size. It pushed the edge of technology by weaving in another fruit from NASA's energy efficiency work: composite fan blades. Using those blades shaved about 800 pounds from the engine's mass and yielded an additional 3.5% fuel savings. The engine burned cleaner too, with roughly 60% lower emissions of nitrogen oxides compared with older designs. It ran quiet enough that, as one technical program manager, Christopher D. Clayton, said, "The whistle of wind past landing gear might be more noticeable than the roar of the engine itself." Efficiency, he emphasized, was the point. The 777 now flies with an engine that traces its lineage directly back to the E3 effort. Pratt & Whitney's line climbed steadily, if more slowly. In 1988, company reports showed encouraging efficiency trends based on the E3 technologies, along with notes that more work remained to bring tomorrow's gains into today's engines. That arc bent toward clarity in 2007, when Pratt & Whitney launched its geared turbofan on the Mitsubishi Regional Jet, a 70 to 90-seat aircraft aimed at a wide market. Mitsubishi expected to order thousands over the following years, and the enabling ideas, separating the fan from the low-pressure turbine with a reduction gearbox so that each could run at its most efficient speed, and pairing that mechanical change with aerodynamic and materials improvements, could be traced back to lessons and confidence built during ACE. The accumulation of such results, quick wins from ECI and deeper structural gains from E3, spurred a hopeful mood around NASA's aeronautics work. In 1979, Raymond Colliday spoke of early success in one element of the fuel efficiency program and expressed confidence that more of the advanced concepts would follow into production. But optimism must share space with politics, and in 1980, a new presidency loomed with new ideas about budgets and priorities. The very quality that made ECI a favourite, speed, made the other programs more vulnerable. They needed longer spans of time to mature and prove their technologies. They asked for persistence, money, people, and patience measured in years rather than months. 3 years after AC began, voices inside and outside NASA worried aloud. Would the government end a program that, in its short-term parts, had already shown how valuable it could be in making the nation's aircraft burn less fuel? And for NASA as a whole, a question broader and sharper hovered overhead. Would the agency be allowed to continue its work in aeronautics?